Welcome to the deep dive. Today we're jumping into something called the Central Limit Theorem. You might see it as CLT.
Yep, CLT. It's a cornerstone, really.
We've got some specific questions lined up to guide us, and our goal, to figure out why this theorem is so foundational in steps. What does it actually let us do?
Right, so, okay, the central limit theorem, what it basically says is, if you take enough random samples.
Independent samples.
Yes, good point. Independent ones. From pretty much any population, it doesn't matter what it looks like initially.
Okay.
Then you calculate the average, the mean, for each of those samples. The distribution of those averages starts to look normal. You know, that classic bell shape.
Wow, okay. So even if my original data is like totally skewed or weirdly shaped,
Exactly.
the means of samples from it will eventually look normal if I take enough samples.
That's the magic of it. Think about how tricky things were before this was understood. Analyzing populations where you didn't know the distribution shape. A nightmare.
CLT gives us a shortcut, almost. That is powerful. Are there conditions, like catches?
Yeah, a couple of main ones. You need a big enough sample size.
How big is big enough?
Well, it kind of depends, but the general rule of thumb you hear tossed around is about 30, n equals 30.
Okay, 30-ish.
And like we said, the observations within your samples need to be independent. One shouldn't influence the next.
Got it. Large-ish independent samples. So why does the original shape stop mattering so much?
Think about averaging. Let's say your population has lots of small values, but a few really huge ones.
Yeah, like income data sometimes.
Right. If you take a tiny sample, maybe you just get small values, or maybe you grab one huge one and it throws the average way off.
Makes sense.
But with a larger sample, those extreme highs and lows tend to balance each other out more when you average them. The process of averaging itself smooths things out and pulls the distribution of those averages towards the normal shape.
Okay, I think I'm getting that. So how does this connect to, say, research? Like testing if a new drug works better than an old one?
Perfect example. That's hypothesis testing, and the CLT is, well, crucial.
How so?
Because the CLT tells us the sampling distribution of the mean, or the difference in means between two groups, will be roughly normal. We know a lot about the normal distribution probabilities, standard deviations.
Right, all that z-score stuff.
Exactly. So we can use those known properties to figure out if the difference we see in our samples is likely just random chance, or if it probably reflects a real difference in the whole population. Like, does the new drug actually work better overall?
Okay, so as we increase that sample size, n, what happens to this distribution of sample means? You said it gets more normal.
Yes. 3 key things. Its center gets closer and closer to the actual population mean.
Okay.
Its shape looks more and more like a perfect bell curve.
Right.
And critically, its spread gets smaller. It gets narrower.
Less variability between the sample means.
Precisely. We call that spread the standard error. Smaller standard error means our sample mean is likely a more precise estimate of the true population mean.
And you mentioned comparing groups.
Yeah.
Like 2 drugs, or maybe 2 teaching methods. CLT works there too.
Absolutely. It extends nicely. If you have 2 independent groups and you look at the difference between their sample means, the distribution of those differences also tends towards normality as sample sizes increase.
So we can test if the average difference is significantly different from 0.
You got it. That's the core of many comparison tests.
Where else is this theorem hiding in plain sight?
Oh, all over. Quality control on assembly lines. They sample items. Opinion polls trying to gauge election results. They sample voters.
Right. They don't ask everyone.
Medical trials testing treatments. Sample of patients. The CLT underpins the inferences made in all these cases.
What about confidence intervals?
Yeah.
That plus or minus 3% margin of error we hear in polls.
Directly related. The CLT justifies using the normal distribution to build that interval. We take our sample mean, use a standard error, which relies on CLT principles, and the properties of the normal curve to create a range.
Where we're pretty sure the true population value lies.
Exactly. The margin of error is basically tied to the standard error and how confident we want to be.
You keep mentioning standard error. Just to nail it down, that's the standard deviation of what exactly?
It's the standard deviation of the sampling distribution of the mean. Imagine taking every possible sample of a certain size, calculating their means, and then finding the standard deviation of all those means. That's the standard error.
Okay, a theoretical standard deviation of sample means. And CLT helps us estimate it.
Yes, and understand its behavior. Larger sample size means smaller standard error, more precision.
One last thing. Sometimes people use the normal curve for things like Coin flips, even though that's technically binomial, right? Heads or tails.
Good question. That's the normal approximation to the binomial distribution.
And CLT is involved.
It's the justification. A binomial outcome, like number of heads and n flips, can be seen as a sum of many independent trials. Each flip is 0 or 1. The CLT applies to sums and averages of independent variables. So if you have enough trials and meet certain conditions,
Like MP and N1P being large enough.
right, then the binomial distribution starts looking very much like a normal distribution, which is often easier to work with for calculations.
So wrapping up, the CLT is this incredibly useful bridge. It lets us use the predictable normal distribution for sample means, even if the original population data is all over the place.
That's a great way to put it. It connects the sample we have to the population we want to understand, often via the normal curve.
It unlocks a huge amount of statistical inference, hypothesis tests, confidence intervals.
Couldn't do modern statistics without it, really.
Okay, so a final thought for you listening. Next time you see a poll result or read about a medical study's findings, remember the CLT might be working behind the scenes. This ability to assume normality for sample statistics, thanks to this theorem, is what allows researchers to draw those broader conclusions from limited data. It's pretty fundamental to how we make sense of a complex world using samples.